Hi there, my name is Paul and this is Exposure Therapy. In this video, I'll explain why your photos of the moon are often overexposed and how you can fix them. I teach group photography workshops and occasionally students will ask some variation of the following question. I tried taking a picture of the full moon last week, but it turned out too bright and featureless. How do I take photos of the moon so that it looks similar to how my eyes see it? My typical and slightly cheeky response is to point out that it's sunny on the moon. Then I wait for a beat or two and let it sink in. Let's begin with the basics. The moon and the sun are the most prominent celestial bodies in the sky. An important distinction between the two is the nature of their light. The sun radiates its light. It glows. It's similar to the flames of a fire, neon signs, and the tungsten filaments of light bulbs. By contrast, moonlight is sunlight that has bounced off its surface to end up on Earth, both in our eyes and in our cameras. Conventionally, the most reliable way to get the correct exposure of subjects that don't glow is by using an incident light meter, such as this Sekonic that I've had for about 15 years. These devices measure the amount of light falling on your subject. I walk up to a subject, point the white dome towards the camera, take a light reading, and the meter shows the correct exposure settings for the scene. However, there's an obvious flaw with this method. With its average orbital distance of about 385,000 kilometers, one does not simply walk to the moon. So what do? We remember that it's sunny on the moon. But let me qualify that statement. Except for lunar eclipses, sunlight illuminates half of the moon's surface at any given moment. However, there's a daily change to the apparent shape of the sunlit portion of the moon as seen from Earth. These differences in appearance, known as lunar phases, occur because as the moon orbits the Earth, we see varying amounts of its sunlit half. The moon is not visible during the new moon phase when it's roughly between the Earth and the sun. The new moon is invisible because it's in the same part of the sky as the sun, and its near side, the hemisphere that's always facing the Earth regardless of phase, is in complete shadow. As the moon continues its orbit, progressively more of its near side turns towards sunlight. First it becomes a waxing crescent moon, then a first quarter moon, followed by a waxing gibbous moon, culminating in a full moon. During a full moon, Earth is roughly between the moon and the sun. The full moon is completely visible because it's opposite the sun in the sky, and the hemisphere of its near side is in full sunlight. The lunar phases continue in reverse beyond the full moon as its near side gradually turns away from the sun. These phases are a gibbous moon, last quarter moon, waning crescent moon, and then a new moon. The period from a new moon to new moon marks an entire lunar month, which takes 29.53 days to complete and is the equivalent to a single day-night cycle on the moon. We've established that it's sunny on the moon and that we see varying amounts of the sunlit hemisphere throughout a lunar phase cycle. But we still have the problem of not getting close enough to the moon to get an exposure reading. The solution, as earthbound photographers have figured out long ago, is taking an incident reading from somewhere that's within reach and has light identical to their subject's position. It's sunny on the moon, but it's also sunny here on Earth. To take pictures, it's entirely reasonable to assume that afternoon sunlight on Earth is identical in intensity to sunlight on the full moon. Therefore, exposure settings appropriate for direct afternoon sunlight on Earth will produce correct exposures of the full moon at night. Anyone who's tried taking photos of the moon at night using their camera's automatic settings has probably found the results disappointing. Most automatic photos of the moon at night are irreparably overexposed, and there are two reasons why. First, the moon is hundreds of times brighter than the surrounding night sky. And second, although the brightness gives it visual prominence, its scale within most photographic compositions is relatively tiny at typical focal lengths. Together, these factors cause the camera to assume it's taking a picture of something that's quite dark, and it compensates by letting in far more light than your intended subject requires, which washes out the moon. The best way to get correct exposures of the moon at night is by taking complete control of your camera using manual mode. But what qualifies as a correct exposure? Even when it's not overexposed, many photos of the nighttime moon render it brighter than its true lightness. In astronomy, albedo describes the average surface reflectance of planets, moons, and asteroids. Albedo measures the fraction of incident light the surface reflects in all directions. The moon has an albedo of 0.12, which means it reflects just 12% of the sun's light. This translates to an average surface lightness described as slightly brighter than old asphalt. In comparison, Earth's albedo averages to about 0.3. The photos taken by the crews of NASA's Apollo landings show just how dark the lunar surface appears in comparison to the astronauts' white spacesuits in direct sunlight. The purpose of the Apollo photos was to create an accurate visual document of the lunar surface, its features, and of the astronauts and their equipment. Since Earthbound photographers don't have such mission-critical constraints, we're free to take creative license in our depictions of the moon. Some photographers choose accurate depictions. Others prefer representations that are brighter than true while ensuring the surface details aren't washed out. And a third group doesn't care because their primary subject is something else, such as the moonlit landscape. Hence, every mention of correct exposures features scare quotes. I believe that within the art of photography, every exposure is correct so long as the result is intentional. An exposure is only wrong when the effect is undesirable. The moon's phase affects how bright it appears on Earth. The illuminated portion of the moon looks brightest during the full moon and darkest during the crescent moon. As our angle of view relative to the sun decreases, the moon's highly cratered and irregular surface forms a greater amount of shadows as seen by observers from Earth. This lowers the surface reflectance of the sunlit portion visible to us. Additionally, the full moon appears brighter due to a phenomenon called opposition surge. It occurs when a rough surface appears brighter when the light source is directly behind the observer. The Apollo missions provide human-scale examples of this effect in their photos from the surface. The surge in brightness is quite subtle due to its gradation and the impact of color constancy. The difference in brightness becomes rather stark when making a side-by-side comparison of two non-adjacent patches of lunar soil. In some photos, the effect is also noticeable on a small scale in the reflections of astronauts' helmets. In this famous example, the opposition surge brightens the area around Buzz Aldrin's shadow as seen in his helmet's reflection. And here, we see it in the reflection of David R. Scott's shadow from Apollo 15. On a macro scale, the entire visible surface of the moon experiences an opposition surge of brightness during the full moon phase. Regardless of the lunar phase, the moon's brightness and color are also affected by its altitude, which describes the apparent height of a celestial object above the horizon. It's expressed in degrees, with the horizon at 0 degrees and the zenith directly above at 90 degrees. The moon appears brighter at progressively higher altitudes. The sun exhibits the same characteristics. Sunlight is harshest at solar noon and faintest at sunset. In both cases, the atmospheric scattering of light causes the effect. Light scattering occurs when photons bounce off particles in their paths, such as atoms and molecules. Particles that are smaller than the wavelength of visible light are more effective at scattering the short wavelength photons of blue light than the long wavelength photons of red light. Light scattering occurs at all altitudes. When the moon or sun is near the horizon, either rising or setting, the light reaching your eyes passes through a thick layer of atmosphere, which scatters a far more significant amount of blue light than red. Since a large portion of their light is scattered away from a straight line path to your eyes when they're near the horizon, they appear redder. At higher altitudes, the moon's light passes through a comparatively thin layer of the atmosphere, scattering just enough blue light to give the moon its characteristic yellowish color, distinct from the stark gray surface depicted in the Apollo photos. As an interesting side note, if you're an early bird, you've probably noticed that sunrises are less red than sunsets. That's because there's a greater propensity for stronger winds during the daytime, which helps lift dust particles into the atmosphere and scatters even more blue light. The same effect doesn't necessarily apply to the setting and rising of the moon. I've personally witnessed many reddish moonrises, however, they've all occurred close to sunset, while dust permeated the local atmosphere. All of this relates to taking photos of the moon. Exposure settings derived from mid-afternoon daylight are generally correct for pictures of a full-ish moon at an altitude of 45 degrees or greater, that is, more than halfway up between the horizon and the zenith. However, these settings will likely be incorrect for photos of the moon while it's near the horizon, since Earth's atmosphere attenuates much of its brightness. Have you ever gazed upon a crescent moon and realized that you could see details in its shaded portion? Much as with the moon, some of the sunlight that strikes Earth's surface and clouds reflects into space. This reflected light is called earthlight. The subtle illumination of the moon's dark side by earthlight is called earthshine. The distinction between the two terms can be quite confusing at first, but it's all quite simple if illustrated with a diagram. Light from the sun is sunlight. Sunlight reflected by the Earth is earthlight. Earthlight reflected off the moon's dark side is earthshine. Earthshine is most prominently visible during the moon's crescent phase. An observer standing on the moon's near side would see a very bright gibbous Earth against the black sky. At this point, you should come to the gradual realization that the moon experiences Earth in phases, and these phases are complementary. Thus, a new moon on Earth coincides with a full Earth seen from the moon, and so on. Earthshine peaks during the new moon, but remains invisible because of the moon's proximity to the sun in the daytime sky. Taking photos of Earthshine using your camera's automatic mode should give decent results because Earthshine is closer in brightness to the typical night or twilight sky. However, a single exposure can't capture detail in both because the difference in brightness between Earthshine and the sunlit portion of the moon is too significant. Against the dark sky, your camera will overexpose the crescent. The point of this video is to explain the futility of a single solution. That's because the moon's brightness varies with its phase and altitude. Moreover, the accuracy of your exposure to the moon's true lightness is also an artistic decision. The solution requires internalizing a fundamental principle. It's sunny on the moon. However, for those of you inclined to prescriptive recommendations, start with exposures appropriate for the full moon high in the sky and incrementally work your way down to dimmer moons. Select manual shooting mode and choose appropriate exposure settings for a subject in direct afternoon sunlight on Earth. At ISO 200, this means selecting f5.6 and 1/2000th of a second, or f8 and 1/1000th of a second, or f11 and 1/500th of a second. All of these different settings produce the same exposure. When the moon is lower in the sky or during a minor phase, increase your exposure by selecting a lower f number or slower shutter speed, or both. Experience and practice using your camera make the process faster and easier. However, it would help if you started from the principle that it's sunny on the moon. I hope you found this video interesting and helpful. I enjoy talking my students through these types of questions instead of stating the correct settings without explaining why they're right. If you have requests for topics, let me know in the comments and I'll consider them for future videos. In the meantime, you can learn more about photography or join my group workshops in Toronto by visiting exposuretherapy.ca. See you next time.